transformed responses. In other words, just basic solutions of state equations for different kinds of insights. So many of the formulas that you will see, you will recognize. Maybe some of them will be new to you, because that's where our contribution has been. Okay. Responses are readily implemented numerically as well as symbolically in a programming environment like MATLAB. So these are basically just solutions as a function of time. It's important to relate our responses to numerically suitable for small systems, this will be presented in textbooks, like on control systems, to numerical procedures used in routines for larger systems. And we think about this from an educational point of view. So this works fine for systems like of order of n equals 15 or 20. Many of the control problems that we work on are of a lower order than that. And it's also good to take a look at formulas just in order to understand what goes into them and what sort of drives them, if you like. Okay, we're having some problems again. So we focus on expressions for the convolution integral for the matrix exponent to any j greater than or equal to 0, so you can have like a power of 10 or something. We're also going to consider sinusoidal input, and we're going to consider mu of t as a general function replaced by a piecewise constant. For example, like this. So if I can compute x of t right here at this point, I use it as an initial value. And then it's subject to this step. And I can go directly from using x of t here and this step to computing x of t here. So that becomes my next initial value. In one step. There's no numerical integration here. It's just one step of computation. So that's my next initial value. Then it becomes subject to this step. And then I compute x of t right here. And so on and so forth. X of t here is the initial value subject to this step. And I compute x of t right here. Now, where would this be practical, this kind of input? For example, if you have a large process and you're selecting data from different places, it may be such that you're sending your data over Wi-Fi, so your sampling time is not constant. You can have any sort of time in between here, and the steps may be in any sizes, plus. We also consider when we have like a trapezoidal approximation here in between points. Okay, that's the second one. And then the third one that we do is if we approximate in between with a parabola. But then I need an additional value in between here. So, like from here to here, with a parabola, it looks something like this. And I need value in between. Okay, so that's the piecewise constant, the linear approximation, or the trapezoidal, or the quadratic approximation. Now the closed forms themselves, they depend on expressions for the matrix exponent times the vector b. So we will focus on deriving those. And then the derivative of that matrix exponent times b, and the antiderivative of the matrix exponent times b. So we need to develop closed form for all these before we can do the final closed forms. So we consider two types of expressions. Closed form expressions based on the characteristic equation for x equal to a, x dot equal to ax, its roots and the fundamental solution of the corresponding nth order scalar differential equation. So we're going to link everything we do to the fundamental solution of the differential equation. And along with its derivatives and the antiderivatives that form the extended fundamental solution vector, which I will introduce in a little bit. Now, this is suitable for expressing responses to all systems symbolically, as well as to small systems numerically. And so these tend to become unstable for systems of size n equal to 15 or up to 20. So now maybe some of you can answer my question, and I have debates with my co-author about this all the time. I say, okay, these are closed form solutions. Computers will get more accurate and they will get faster. And he says, no, not necessarily. Is that true? Anyone? Are we reaching some sort of a... Yeah?
The computation power will always be limited. It cannot exceed without to a certain limit. And I think is that we have reached that limit in a single processor chip or on a single core.
Yeah.
So if you want to increase the computation power, all you have to go to do is that increase the cores. Mm-hmm. That is the only one solution that is we are working with.
Yeah. So and then if you can compute accurately enough, we may be able to raise that number here. But I don't know. Time will tell. We don't know everything always. We also present analogous matrix expressions based on standard Taylor series approximations for e to the power at. And these turn out to be numerically stable for much larger systems, all the way up to at least 256, which is what we have did so far. Okay, the outline then of the rest of the work. This was sort of like the motivation, why we're doing this. And I've actually been working on this for quite a long time, for more than 30 years now. And I did a lot of engineering stuff, and then it sort of settled on to that I'm doing applied math, but it's sitting really on control systems as a basis. And I always liked math, from the very beginning. So I feel quite good there, and together with my good co-worker, it's been quite a good journey. So the first thing we'll do is the extended fundamental solution vector. It includes the fundamental solution, its derivative, second derivative, all the way up to n-1 derivative. Once we have that, we will derive a closed form expression for e to the power at, then e to the power at times b, and then its derivative for positive k and for negative k. So this will be like the derivatives and the anti-derivatives. We will then do corresponding Taylor series, matrix expressions, move on to expressions for closed form responses to different types of input. I will end up with nice little formulas for CISO systems. We're working with MIMO systems in general. And those have some nice expressions. And then finally move on to conclusions. So let me go quickly through this, because this is material we all know. The characteristic equation is denoted like this. It's associated with the n times n matrix A, and the roots are the eigenvalues of A. We associate with A the fundamental solution of the corresponding differential equation. So it's this differential equation satisfying these initial conditions. So the fundamental solution of this we denote with y sub f of t. And that's sort of a key thing in this presentation. Now, we would like to know how this fundamental solution relates to the impulse response. As engineers, we know the impulse response quite well. And the relation to the impulse response is the following, that the fundamental solution is identical to the impulse response for positive t. So this is the differential equation with the impulse. The two differ for negative t, since the impulse response is 0 for negative t, whereas the fundamental solution extends continuously for negative t. It just satisfies these initial conditions for at time 0. But it's alive for negative t and it's alive for positive t. And that's fine for the matrix exponent, because the matrix exponent needs to be alive for positive t and for negative t. Okay, so here we go to the fundamental solution vector. It looks like this, so it's the fundamental solution. It's the first one. It's differential, and then all the way up to the n minus first differential. And this vector turns out to be a major player in the expression for the matrix exponent times t and its derivatives. So we therefore begin by presenting an effective method for calculating this fundamental solution vector that is readily implemented in a programming language like MATLAB. It has 3 roots, and we have 3 guys here, and so on and so forth. Now, you all know this formula. That's how you compute the partial fraction expansion. This can also be calculated effectively by the following less known recursion. It looks like this. And this was derived by a master student some years back. Becky, that was his name, he did a very good master's thesis. And by the end of the thesis, we asked him, what are you most proud of in your work? And he said this formula. So, it's a nice one. We published it in a paper for 15 years ago, or maybe 20 years, I don't know. So here we come to the fundamental solution. We introduce the exponent vectors. So if the eigenvalue is not repeated, it's just this guy, and then these are added on if we have repetition. We stuff this up in a vector like this. So the exponent is a column vector. Then the fundamental solution is actually given by, and this is obviously well known, the inner product of the partial fraction expansion vector and the exponent vector. Now, we next introduce the Jordan matrix, which is also well known, and that turns out to do the derivatives once we start to do that. So the first one is the diagonal Jordan diagonal block matrix. It looks like that. And then the corresponding n times n block diagonal Jordan matrix looks like that. We note that the derivative of the exponent the entire vector is this Jordan matrix transposed times E of t. So very simple to compute the derivative. And then we can calculate the derivatives of the fundamental solution like this. Okay. So it's simply differentiating E of t, and then we get these, and we can write them up like that. Now there's a fundamental solution vector. We can then write in what we just had on the previous slide. And we can also work this around a little bit, like that. And then we can write this as an n by n matrix. We call it kappa times the exponent vector. So kappa looks like this. And this is valid for all lambdas, positive, negative, zero lambdas. So the fundamental solution vector is kappa times E of t. And remember this. Now the antiderivatives, we need to extend the definition of the of the derivative to negative k values. And so we do that simply like this. And in the case when lambda equals 0, then we must make note that our corresponding exponential has to be replaced by this vector. Okay? So just be careful when you have a 0 eigenvalue. You just substitute that in to the corresponding step of the exponent vector. Now we also have another problem because we're actually going to do the Jordan matrix inverse k when we do the antiderivative. So we need to interpret, or if you like, look at this as an operator, like this. So you also similarly just plug that into the appropriate place. So then we have the extended fundamental solution vector. We did it to include all derivatives and antiderivatives valid for all lambda I. And if we just look through these briefly, they first look like that. The only difference here is that we have the Jordan matrix to the power k all the way down. And we can write this like that if we want to. K may be either positive or negative, including all possible values of roots in the characteristic equation, but with appropriate amendments in the case of negative k and 0 roots in the characteristic equation. So let's go to the computation of e to the power at for the controller form. If you're a controls person, if you're a mathematician, you call this the companion form. You recognize this immediately. It's a very sparse one. It has a 0 column here, an identity matrix here, coefficients of the characteristic equation in the reverse order with a negative sign in the bottom line. And I'd like to define this notation. So dot 1 means the first column of this matrix. That's the second column and the nth column. And it turns out that we can actually prove that the last column of e to the power ACT is the fundamental solution vector. And then we can go backwards and compute the other columns of e to the power ACT from the fundamental solution and the coefficients of the characteristic equation. And this is actually proven in our 2018 ACC paper. Now, from this and the fact that we know that this holds, if I differentiate e to the power any matrix exponent, I can either write it like A times the matrix exponent, or in this order, it follows that the first row, so the first line, is a Hankel matrix times the fundamental solution and the whole thing transposed. The Hankel matrix looks like this, so it's a constant on these diagonals, and that's an in fact, this is 1. And then we have the other coefficients of the characteristic equations, all the ones except A0 is excluded here. So an upper triangular Hankel n by n matrix comes in here. So that's how we can write the first line of this. Now, the Cayley-Hamilton theorem, you know the Cayley-Hamilton theorem. It says that we can write the function of any matrix, not just the exponent, by using just a sum of some coefficients, and if we're talking about the function of t, then the coefficients are functions of t, and then we only need to use a to the power 0, a to the power 1, all the way up to a to the power n minus 1. We don't need any higher up than that. So that's a very well-known result, of course. We've shown in our 2018 ACC paper that the coefficients here in the Cayley-Hamilton theorem, they are actually the first line here, which we just had on the previous slide. So it's a Hankel matrix times the fundamental solution vector transposed. Likewise, the connection between the matrix exponential, and now I'm not just talking about the controller form or the companion form, just the general form of the matrix, looks like this. So we do a sum, and then we take the first line of the Hankel matrix times the fundamental solution vector times the identity matrix plus the second line times the fundamental solution vector, so on and so forth. So that's the ith row, I plus 1th row, or in the Hankel matrix H. So now that we have e to the power at connected up to the fundamental solution, we now move on to this vector, which is e to the power at times the vector b. So that becomes simply that. And if we massage this a little bit, it's not very difficult to do. We can see that we can actually write this as the controllability matrix times the Hankel matrix times the fundamental solution. So this is the standard controllability matrix here. So that's a nice little form for this expression. We then have the derivative of this vector. Obviously, these are constant matrices, so we only need to differentiate the fundamental solution vector here. Okay, there's a reason why I put a parenthesis on these two matrices, and it turns out that numerically it's better to multiply them together and work with that in a particular algorithm, as opposed to doing the controllability matrix times the Hankel matrix. So I'll show you the algorithm. It's just a very simple. So this is a side note. The computational issue of the controllability matrix times the Hankel matrix is that it's better to do it in a recursive algorithm like this. So we begin with B, and then we move through with the A matrix and the coefficients of the characteristic equations and the B vector to form all the other columns in this product. So that's why we write it like this in the SQL. So we don't compute this times that, we compute it in this way. So now we're up to the antiderivative. The antiderivative, we can write it like this, and then we can derive that it's actually this expression. It needs to satisfy these conditions here at t equal to 0, and it is readily verified that this expression does satisfy these, noting that the differential, this is just linearity here, the differential of the ith derivative of yf is I plus 1 for all I. Okay, so I told you before that they work pretty well for any to 15 up to 20, but for larger systems we have numerical problems. So we also did a presentation or computation of how things turn out when we use just a Taylor series expansion for the matrix exponent, so that goes up to infinity. But the thing is that this guy here, the I fractional, kills down the terms fairly quickly, so we don't need to compute that many of those. We do this subject to norm, which when it's we continue to compute while this is greater than some epsilon, and then we stop. And it turns out to be fairly quick, and so we did some experiments with that, and that turned out to work well up to n equal to 256 at least. We have not tried larger numbers. Okay, now if I want to do the derivative of this guy, I use the same algorithm as on this page. You see how it's initialized here with b, and then we go through here, computing these terms, we add them up, and then we stop once we're done. To compute the derivative, we just begin with this guy, okay, and then it's the same thing we go through. Oh. So I'm told I have 5 minutes back, so I better speed up, I think. Here's the impulse response, and let me just point out what it looks like. It looks like this. So it's this controllability matrix times the Hauksdottir times the fundamental solution. And then as an infinite series, it looks like that. Here's the step response. Okay. Here's the ramp response. All right. And the general polynomial response looks like this. You see that these hold true. If you just differentiate this one here, you get down to the other one. Sinusoidal responses. So this is our system. We have some x of 0 here, and we do the convolution integral, and it's fairly easy to show that this expression holds for the sinusoidal input. We can also write it like this, and these are easily proven by integration by parts. For general inputs, we want to be able to compute this. And so that's what we were talking about earlier. We get an x of t, delta t can be any size. We go through one computational step, and we get another x of t, and so on and so forth. So delta t does not need to be fixed, nor do the steps have to be fixed. So we can do it like that. This is the same slide we had earlier. I call this asynchronous step inputs. That's the result for that. So here you see what it looks like. Okay, easily computed. That's the Taylor series expansion version. Okay. Here we do the linear interpolation. We have this result and the parabolic interpolation, where we need an additional value here. Okay, there is one thing important to tell you here. It turns out that the linear approximation based on the Taylor series results in a procedure that is equivalent to MATLAB's LSIM with regard to accuracy, stability, and execution time for steps. We never knew exactly what was behind LSIM until we figured out that that's what it's doing with this approximation. If we move on to the quadratic approximation, it allows in general much larger step sizes than the linear approximation, but we require additional input values in the middle. Okay, 2 more slides and then the conclusion. This is one of my favorite results. So we're now into seesaw systems. So okay, this is the differential equation. And then if we work with the controller form or the companion form, it looks like this, and then we have only the coefficients of the differential equation in this result. So it looks like that. We have the numerator coefficients here in front, and then we have this sort of controllability matrix, Hansen matrix, fundamental solution, and then the convolution integral. And another favorite result is we can write the seesaw result like that, and in that case the Markov coefficients, they appear here in front. Okay? And so to the conclusions, we have written MATLAB programs for all the responses presented in this lecture, and as I said earlier, the form is good, n equal to 15 to 20. The Taylor series at least 56. We iterate, however, that from an educational point of view, we consider it to be valuable to relate in this way expressions for small systems like those presented in textbooks in control systems to numerical procedures used in routines for larger systems. And in that case, the Taylor series expansion is simple. Obviously, there are more sophisticated algorithms than that, but these are easy to understand. And when you're beginning to capture these things, that's important. So, how much time did I take? Thank you so much, ma'am.